All right, so we're going to start with a single logarithm that we got to express in terms of a log base b of x and log base b of y. So if you look at the logarithm, the single logarithm as it's written, you've got log base b of x squared y. What we have that's being plugged in the logarithm is a product. So because that's a product, I'm going to apply my first property right here that allows me to split up that product and create some addition. This would equal log base b then of x squared, that's the first part of the product, plus log base b of y, because that's the second part of the product. And I'm trying to express this in terms of log base b of x and log base b of y. I've got log base b of y over here. This is not yet log base b of x. Right, it's log base b of x squared. So the question becomes, what do you do with this 2? Well, you go back. I see I've got this power that's applied to this little base here. I can bring that power down to the front, apply that last property. That would give me a 2 now in front of this first logarithm, which is log base b of x now, plus log base b of y, which remains unchanged. All right, on the first one, you got log base b of a quotient. So out of those properties we have listed, this would be the second one on the list. I could break up that quotient, make it log base b of x, my numerator, right? Then it'd be minus, since it's a quotient, log base b of y. Now that y is to the 4th, right? But what's going to happen with that power of 4? Okay, it's going to go in front of the function for the logarithm. So I could just bring that down, put it in front. That'd be my simplified answer, right? On part B, because we can make connections to powers here, right, with these logarithm properties, it might make more sense on B to take this root out of it and raise this xy to the 5th that's contained by that root to the 1/2 power. If you do that, you can take that 1/2 power, right, and you can bring it down to the front, right, because that's that last property on the list. Now, when you bring that down to the front, looking at what would remain that you're taking the logarithm of, you've got a product there that you'd have to split up. So this 1/2 that's in the front would have to be attached to each logarithm as you split it up. So you'd have 1/2 log base b of, first part of this product is x, plus, we could say 1/2 log base b of y to the 5th, but that 5 we'd be bringing down to the front. If there's a 1/2 in front, we're going to multiply that 5 on. So instead of saying 1/2 here, probably make more sense to say 5/2. That's how that one would simplify. All right, last one. I see this 1 over some quantity raised to a power. Hopefully we've done enough problems now where we're thinking reciprocals maybe, we're thinking negative exponents could help, right? Maybe I take this out and make that a -3 instead, right? So it's log base b of this quantity raised to the -3rd. It's kind of like part B now, where I could take this -3 and bring it down to the front. You'd have a -3 then in front of each of these logarithms as you split up this product. So it'd be -3 log base b, first part of the product is x. You'd be adding on, but there'd be a -3 in front, so I could say -3 log base b of the second part of that product, which would be y. You express the logarithm as a single number. I'm sorry, express the logarithm of a single number. What that means, go in the other direction. If we know that we're adding a couple of logarithms here, well, we know that we can probably form a product somehow, right? That would help us condense down to a single logarithm. But before I do that, I might want to take note of any numbers that are sitting in front of logarithms, because I know those numbers get there because originally they were powers, right? This 2 in front, I could bump that back up. Yeah, that's always the first thing I do on these problems. If there's a number sitting in front of a logarithm, bump it up as a power. Once you bump that up, and you know that you got 3 squared here, which is obviously 9, because of this addition, we can create a single logarithm where we are taking the 5 from this logarithm and multiplying to the 9 in that logarithm. 4 times 9 gives us 45. There's your single logarithm of a number. So if you try to make sense of part E now, always a good rule of thumb to follow, start inside parentheses. If I start inside parentheses here with the logarithms involved, there's no numbers sitting in front of them, so no powers to raise, just the addition. Because it's just the addition, let's see, I've got log base 7 of 24, that's unchanged, minus, well, this addition right here, if I put this together as a single logarithm, be log base 7 of, you've got 2, you've got 3, so you're multiplying that together to get 6. Now with those 2 logarithms that remain, because of the subtraction, we know subtraction gives us this quotient idea for a single logarithm. So I'll write this as log base 7 of 24 divided by 6. So log base 7 of 4. There's your single logarithm of a number. All right, on F here, I can actually evaluate this if I put it together because of the subtraction. Right, the subtraction is telling me that I can take this 40 and this 5, I can divide it. So I have the logarithm of base 2 here. 40 divided by 5 is 8. So it becomes log base 2 of 8. Log base 2 of 8 is something we can figure out, because all log base 2 of 8 means is I need to find the power that I'm going to place on this 2 to get to that 8. Right? 2 to what power gives me 8? 3 does, right? So 3 is my answer. On part G, you know, if we've got parentheses, you may just want to start inside there. That's fine. As we discussed before, if you see a number sitting in front of a logarithm, might want to bump that up as a power. So I see this 5 right here in front of the logarithm. Might want to bump that up there. Okay, if I spell out what all this means inside the parentheses, you got this 1/3 that's being multiplied to the result. Well, inside here, if I want to put all this together, it's going to be log base 4, right? The addition means I'm going to multiply the 10 and the 2 to the 5th. Now, 2 to the 5th is 32, right? So I'm going to take 10, I'm going to multiply to 32, get 320. The minus means we're going to divide by 5. So you know what 320 divided by 5 is? Try 64. Notice what happens. You've got a logarithm here that you can evaluate. You could also take this 1/3 if you wanted to and bring it up as a power, but really, if you just take 1/3 and multiply to log base 4 is 64, which would be 3, right? Because 4 to the 3rd power is 64. If you take 1/3 of 3, your answer is going to be just 1. Okay, on part H, we'll just be consistent here. Start inside the parentheses. Any numbers sitting in front of logarithms, let's bump those up. Now, I'd be cautious of this negative here. Go ahead and leave this as subtraction as you take this 1/2 and bring it up. If I bring that 1/2 up, think about what that 1/2 means. That 1/2 means you're taking the square root of 100, right? That's what that means. So you've got a 4 in front. inside, we've got log base 5 on each of these logarithms. And the subtraction means I'm going to divide. I'm going to divide this 2 by the square root of 100. So square root of 100 being 10. 2 divided by 10. If you take 2 and you divide by 10, you get 2/10 or 1/5. Okay. So with this 4, you could bump it up as a power if you want. Or you could take 4 times whatever log base 5 of 1/5 is. Well, let's think about our exponents here and how they work out, right? Because after all, logarithms are just exponents. If this was just a 5, 5 to the first would give you that 5, right? So this logarithm would be 1. But this is not a 5, it's a 1/5. That's a reciprocal, right? So to note reciprocals with exponents, what do? Yep, make it negative. 5 to the negative first would give you 1/5. So 4 times negative 1 is negative 4. All right, so solving an equation now, kind of putting it all together. Still applying these properties to help us out. Whenever you have logarithmic equations, your goal is to try to condense these logarithmic equations down as much as possible where you got single logarithms to work with. If you can just work with one logarithm at some point, great. If not, at least get it to the point where on each side you just have one logarithm. So notice on this problem, the way it's set up, we've got addition. So we know that means I can take whatever I have the log of there, whatever I have the log of here, right, and multiply those pieces together. To make this log base 4 a single logarithm of x times x minus 6. Now, if you want to go ahead and multiply the x through, make it x squared minus 6x, that's fine. That actually is helpful. Because if this all equals 2, you've got a single logarithm that equals a value. We can go back to riding the merry-go-round, rewrite this in an exponential form. Rewriting this in an exponential form, you've got 4 to the second equal to x squared minus 6x. Obviously, this is a quadratic, so to solve the quadratic, 4 squared being 16, we got to subtract over, leaving us with 0 equals x squared minus 6x minus 16. Either factor to solve or use the quadratic formula. This is factorable. It factors to a minus 8 and a plus 2, right? Meaning your answers for x, well, x minus 8, if that equals 0, x is 8. X plus 2, if that equals 0, x is negative 2. Now you do have to be cautious when you're solving these. At the end, just like you can do with any equation, whether it's logarithms or not, you can take your answer, plug back in and check, right? Here you definitely need to do that, because if I take this 8, let's say, and plug back in here, I've got log base 4 of 8. Plug back in here, I've got log base 4 of, this would just be 2. What I'm taking the log of for both of those is positive. That's a good thing. That works. But if I take this negative 2 and I plug in, log base 4 of negative 2, log base 4 of negative 2 minus 6, so negative 8. Because I'm taking the logarithm on at least one of these of something negative, this negative 2 actually does not work. The rule with logarithms is you can only take the log of something positive. If you plug back in and you're taking the log of 0, or you're taking the log of something negative, you've got to take this solution out. X equals 8 is your only answer here. All right, so we finish here with logarithms just everywhere, right? If you look at this first equation, notice some things like the 3 sitting in front of this logarithm, so hopefully we're in this habit now where we bring that 3 up. I see how the logarithms are being added, so maybe put these logarithms together, say log base 5 of, it'd be 2 to the 3rd times 4, so that's 8 times 4, 32. That's going to equal over here log base 5 of x. Not much you can do with that. What's really nice about this equation compared to the last one is you've got logarithms on each side with the same base, which is how these problems are going to be set up anyway. Since they have the same base, that means whatever we're taking the log of on each side, those two things must be equal. So we don't divide logarithms out, we just kind of drop them out. Use a little common sense and say, all right, these pieces here, they must be equal. In this case, x equals 32, so you're done. So on k, same kind of thing. On k, because I've got a 2 in front of this logarithm, I want to bump that up, make this x squared. We're adding on this side, we're adding on this side, so we can bring these logarithms together on each of their respective sides. Over here we'd have log base 3 of 36 times x squared. And over here we'd have log base 3 of 18 times 8. What's 18 times 8? Check me, I think it's 144. Once again, you got logarithms with the same base on each side. Everything's equal. So whatever trails these logarithms, in other words, whatever's plugged into these logarithms, they must be the same. So 36 x squared equals 144 as we drop the logarithms out. Divide both sides by 36 to isolate that x a little bit better. 144 divided by 36 should be 4. Okay, when you take the square root of both sides here, you're solving, so you got to remember that plus or minus is involved. However, if you go back to what I just mentioned a couple problems ago about taking these answers and plugging back into check, you will notice that if you take -2 and plug back in right here, you're plugging into the initial form, right, which was log base 3 of x. You'd have log base 3 of a -2, and that can't be possible. So your only answer here is +2 for x.